Today, we are glad to have Dr. Christian Froeck, our customer support engineer based in Germany. Christian has obtained his PhD at University of Dresden with the research topic in situ electrochemical scanning probe microscopy of the deposition of conducting polymers. After he did a postdoctoral at the Institute of Polymer Research Dresden on AFM on polymer, with experience in scanning probe microscopy for more than 25 years. Christian has been working as customer support engineer at Bruker for more than 13 years. For our today's webinar, Dr. Christian will talk about the key parameters as deflection sensitivity, tip radius, spring constant, and also discuss the probes needed for a good experimental setup. At the end, we will have a 15 minutes Q&A session for you. We will also send you by email the presentation slides and the webinar recording. Okay, let me pass the wheel to Christian. Please go ahead.
Hi everybody, this is Christian Froeck from Bruker, Germany. So yeah, nice to have you all here. My main problem is that I can only hear the moderator. So there's no direct feedback, but again, at the end, we will have a question and answer session. So let me start with PeakForce QNM part 1 about force curves and how PeakForce QNM works in general and what are the key parameters. It is mainly a presentation by my colleague Yungming Hua from Santa Barbara. I did some small adjustments to it and also try to include later some live images to show you where the problems can occur in PeakForce QNM. Okay, what is PeakForce QNM? It is an imaging mode that produces height images and in addition quantitative non-mechanical property images at the same time. So you can have your height information and also something like the modulus of your surface or an adhesion map as well. It splits off in two parts. One is the PeakForce tapping part. So this is for the scan assist part, where basically the system adjusts itself in the first approximation for good scanning conditions, which is used to image the sample surface. And you have, in addition, the QNM part, where you use the PeakForce tapping mode to create force curves, and from these force curves you derive quantitative material property data. So how is this the force curves are obtained in general? So basically you can see here on the first image here or sketch, when the probe and the cantilever are approaching the surface at a certain distance, the surface and the tip feel attracted to each other due to van der Waals forces or other attractive forces. And then there would be something like a snap into contact. If you look on the right-hand side where you can see the retractor and approach force curve itself, you would start out on the left-hand side where the blue is basically behind the red right now. And you wouldn't feel any, the two surfaces do not feel any interaction or attraction. But at a given point here, number 2, basically you have this snap into contact, which is a mechanical instability more or less. So that's not a linear behavior. It's an unstable behavior. And then the cantilever would still bend further. You can see that the cantilever on point 3, the cantilever deflects more, and while the substrate is further going down, so you would press in against a hard wall if you have a hard substrate and a stiff cantilever. So the deflection is at that point not so prominent, but you also can see that you have some slight indentation into the surface. However, it's like pressing your arm or hand against a hard wall, where this behavior here is linear. And then you, at this point, number 3, the forces at maximum. After that, the cantilever is moved upwards again, but it stays in contact with the surface, and due to the attraction forces and adhesion behavior, basically it bends the other way around. So it's a much stronger force. Usually it is. And then at a certain point, then again, it would snap off into the air, and then again, there would be no interaction again. So these are the typical steps in a standard force distance curve. Here you can see two different ones obtained. This is the one more or less we discussed just in the previous slide. The other one looks different, and here you can see different behavior. You would also see here on the right hand side the snap in, and then instead of a straight hard wall contact linear force, you see the bending here, and then if you go back, if the cantilever is removed from the surface, it's still you see it's a curved structure, and then here also you can see the adhesion is not as sharp as on the left hand side. This is due to mainly elastic deformation of your and plastic deformation of your surface. Here you can see we are talking a bit more about the adhesion force. So the minimum deflection point on the retract plot, so on the red curve, is the maximum adhesion force, and this would be then later used for the quantitative nanomechanical mapping. However, without a calibration, the ramp curve itself is giving a deflection signal versus Z, meaning movement of the Z piezo. And the deflection raw unit is, because we are using a photodiode here in the AFM, is in volt. The question is then how to convert deflection from volt into nanometer, basically by calculating the slope here. So how many nanometers would correspond how many volts shown in the photodiode. And then the final question is then, because we are talking about force curves here, is how to convert deflection in nanometers to forces in nanonewtons, for instance. And there the answer is more or less simple. So if you know the cantilever's spring constant, which gives you exactly how much it deforms on what forces, you can derive there the nanonewton, the forces, which brings me to the Young's modulus. So one of the channels we measure is the so-called DMT modulus, or Young's modulus. So this is the elasticity or hardness of your surface when you apply pressure to it. So basically it's the tensile stress divided by the extensional strain. Here's the formula for it. Overall, it is, again, you apply a force to a given area, and the change of height of this area when you press on it, it is in correspondence with the overall length, and from that you derive the Young's modulus. Here are some values for typical materials, like rubber is very soft, 0.1 to 0.01 gigapascal, so more or less in the lower megapascal range. Teflon, like half a gigapascal. Polyethylene, low density, for instance, 0.1 to 0.5 about. And these are values more or less from literature, so there might be differences and other values you can find in other sources or references. Typically in our sets, we shipped out with the systems, the icon system or the multimode system. We have some sapphire in there. We have fused silica in there. We have a sample of polystyrene in there. We have HOPG in there. So some things you can try then with your system to try to measure similar values here. Overall, the sample modulus is then one of the theories, and this is one of the oldest ones, using the model by Hertz, where basically the idea was to have a sphere interact with the plane, and his model is valid if the contact area is much smaller than the radius of the sphere. And the Hertz model also didn't take into account adhesion forces, mainly because it was a macroscopic model, but it fits nicely also for the smaller regime where we see it as with an AFM. As soon as you are adding adhesion forces to the calculations, then we use the Yagin-Muller-Toporov model, the DMT model, which is directly displayed in our software. There are many more available, and one more I'm coming on the next slide, but before that, so Hertz can be used, it is a linearized model, and therefore it is robust, and there's no need to find actually the point of contact, so the snap-in, it's not needed. In this case, if you look for the Snedon model, which is more recent as well, we are not using a sphere against the plane, but a cone against the plane. And here, this is used usually for larger sample indentations, so softer material, more or less like biological samples or gels. It uses, in this case, the approach curve, so when the tip goes towards the surface, not when it's in contact with the surface, and it includes also plastic deformation, which is not part of Hertz or the DMT model. Here's something about the indentation depth, so basically how much you push into the surface. So again, the scanner would move down and you would press into the surface, and you have, in our case, with an AFM, you always have during contact, the movement would cause a cantilever deflection and a sample indentation, so both at the same time. So both cannot be directly separated. You can do that later, so basically by software, where you say, okay, the separation is the Z movement, subtracted by the deflection change, and you use the actual travel position with the maximum indentation as point as a reference. For that, the indentation depth is the amount of separation change after the initial contact, and it always should be positive. One thing about that is, so if you realize that in your measurements, we have, depending on the software versions, something like the deformation depth is shown, which is the combination of, again, cantilever deflection and sample indentation. But also this should also be positive. If the values there are negative, more or less, then this means that your calibration of your system is not made correctly, or you're using the wrong tip for the measurement. Here you can see the force versus distance, what the system is technically recording when you were doing the measurements in the force curves. But we would need the force versus separation. So the force distance curves needs to be converted into the force separation before fitting it with the models like here. So this would be, we need to have actually this value and not this value. So this is one of the things we have to take care of. Luckily, our software is doing that. Simply by our software itself, you can separate that and this in our software, where you basically import the one force curve and then would set up your measurement, your display mode to PeakForce deflection versus separation to have your forces versus separation display here. Here are some examples of the separation curves which can occur when you do this offline. So the above force versus set curve is obtained by a soft cantilever ramp on a very hard sample. For example, a scanner's air probe on Sapphire, and you can see, depending on how you would set up your offline analysis, you could end up with, from this curve force versus Z, to 3 different extreme cases where force versus separation. And basically here you have to ask yourself what is the right one. So let's go from the number 1 here. Basically here the indentation, the snap into contact, is at the 0 position, so this is most probably not correct. Or there are cases when you do the separation selection incorrectly, that you have even here a negative slope, which is completely wrong. You can see even that indentation and adhesion force are also on the negative side, which makes completely no sense. So the only thing which is possibly correct is the number 3, where you see, hey, I have my snap into contact at a positive value here, about, let's say, 8 or 9 nanometers, and then we have our straight wall contact, and then it goes back. So just when you do the offline analysis, be aware of that the curves might be wrong because of your settings. How to get the modulus from a force curve would be using here the DMT model, the new software version. So I think it's software version nanoscope analysis 1.8 and higher, has actually an indentation analysis included, where you basically then set up your parameters here for the your limits, and inside this limit we do a linearized fit. You have to, for DMT again, which uses the adhesion as well, we would include the adhesion force in the offline analysis here. We would use overall, say, okay, it's a spherical contact between the tip and the surface, and then we derive their Young's modulus and the reduced modulus. In this case, around 3 to 5 megapascals. So this would be a measurement most probably on the PDMS, which is included also in the PeakForce QNM kit, which is shipped with the system when the option is purchased. If you would work with a SNED-on model, and here it depends on the radius. Sorry, not on the radius, but the indentation should be much larger than the tip radius. And we would here use not the approach curve, but the retract curve. Also would fit with a linearized model. You don't include the adhesion, but you would use here the SNED-on, the conical fit, and then you set your region here, and then you would get your result here for much for softer materials. Again, usually the indentation is much deeper than on the DMT model. Rule of thumb, just before I forget, is for DMT modulus, your indentation depth should be somewhere between at least around 5 nanometers, can go up to 20 nanometers. Everything deeper, or say where the indentation depth is bigger than 30 nanometers, you should use the SNED-on model. And the SNED-on, again, is used more for biological samples like cells or like gels, where you have very, very soft material. What cantilevers can you select? So what I usually use is actually the upper table, where we say, okay, in the range, expected modulus range between 1 and 20 megapascals, you should use a scan-assist air or similar probe. So the spring constant is around 0.5 Newton per meter. the modulus between about 5 and 500 megapascals, you should use the so-called TEP 150A, nowadays also called AirTespa 150, which has about a modulus, a spring constant of about 5 Newton per meter, between 200 megapascals and up to 2000, so 2 gigapascals. You should use the TEP 300A or the AirTespa 300, it's called nowadays, which has a spring constant of about 40 Newton per meter. Even stiffer in the range from 1 gigapascal up to 20 gigapascal, you should use the AirTespa 525A or TEP 525A. They're similar. They have a spring constant of about 200 Newton per meter. And for the very stiff material, you should use the DNISP probes, so the diamond probes with a steel cantilever. So they have a spring constant of about 350 Newton per meter, and you can measure their modulus up to 100 gigapascals, or let's say roughly 70 gigapascals. If you need to have, if you have material with higher modulus, you would need to use a different method. So that's the maximum we can go with the 350 Newton per meter spring constant on for the PeakForce QNM. For stiffer or samples with higher modulus, we have an option which is called contact resonance. It's a different method, but then you can also measure metals and stiffer samples. However, the cantilever spring constant, and this is really important, needs to match with the sample modulus, meaning two things. So one is you have to have the deflection of the cantilever and you have the indentation of your sample. If you only have, if you have a very stiff cantilever, very soft material underneath, you would just move your tip into the surface, but you don't see a cantilever deflection. So then your system wouldn't work properly. Or put it the other way around, if you have a very soft cantilever, you would have a very soft cantilever and a very hard surface, then it also wouldn't work. I have prepared something for that you can see at least a small hint on that. Let me just try to share my camera view with you. Here we go. Let's try to make it bigger. Here we go. So this is simply, I'm just trying to start a measurement right now with a TEP 150A probe on PDMS. So it's close but not directly there. I think you cannot see the numbers, but basically it says, hey, everything is set to automated approach. So the set point is automatically adjusted, the gain is adjusted, the rate is adjusted, and the limit. So I will just engage right now. And then I would try to point your eyes then to the PeakForce monitor. I will make it larger as soon as we're on the surface. System is approaching. Sorry for the background noise, by the way. We have construction on across the hallway, and I couldn't get the constructors to stop that during the webinar. I'm sorry for that. Hopefully you can still hear me here. Okay, we are still approaching. Here we are on the surface. And as usual, the system itself is trying to find a good scanning conditions under the automated settings, trying to get a good force curve. And you can see here, we'll just make this larger, that you don't get any proper force curve, because in this case, the material is much softer than it could be really nicely measured with the stiffer cantilever. So again, so this would also go for the megapascal range, but again, so if it's if your material is too soft, it will not work. So let me just withdraw and move to a different sample. So trying to do that at the moment. Here we go. Here's the surface. Let's try and engage again with the standard settings. So nothing changed, just a different material underneath. Again, system is approaching. And you can instantly see different material gives you a different force curve. Make it larger, so even now when he's found his way, you can see, hey, I have my point here where I have my snap into contact, and then it goes up to the feedback here. So again, on this kind of material, it's much easier. Just to show you that, try to get a better image in height here. So just making it a bit smaller, that you see, hey, I'm really close to the surface. So I can see the surface here easily. So this is a different material, gives you and different conditions. So this is stiffer, so it works more nicely even in the automated mode. So I don't need to adjust anything in the first approach. So this just wanted to share with you. So this is a good example of using the correct probe on the proper surface. Okay, so let me just turn this off now. I'm coming back to the presentation. So the other method would be to do a calculation here. So for the accurate modulus measurement, the amount of the sample indentation, at least again for DMT, should be 2 to 5 nanometers. Better is 5 to 10. Should be greater than the cantilever deflection. Okay, so PeakForce QNM is slightly different than the force curves again. So this is PeakForce tapping. Here you have a movement like A to B to C to D to E. So A means the probe is about 300 nanometers over the sample, so at a 150 nanometer peak force amplitude. The Z piezo pushes towards the probe. The tip contacts the sample as before on point B. You have your snap into contact, so this is similar. The C piezo pushes further until it reaches the peak force set point, which is number C here. After this positioning, the probe starts to withdraw from the sample, and again it would break free from the sample at a maximum adhesion point, and then it goes back to normal. That is again at 300 nanometer above the surface. So this is a repeated movement from A to E. It's a fixed frequency, usually for nice measurements. As in Scannesis, without the QNM, we usually use 2 kilohertz for that. But what you also can see here, it's not a linear or sawtooth or triangular movement. It's one of the differences. So basically, we use a sine wave as the drive signal, and the triangular wave usually is around 2 hertz, not 2 kilohertz. And since the sine is a continuous, meaning a stable derivative kind of method of function, and the sawtooth is not continuous, so you have the derivative of it is unstable. It is therefore the sine is easier to operate with a feedback. So therefore, the sine wave is the method of choice for a good feedback, which is needed for good measurements. So you would have here something that's called the sync distance. I'm coming to that later. And the feedback versus just a trigger threshold where you would just measure at one point to get it to a certain trigger, meaning deflection on the photodiode. In addition, you can also have a real-time background subtraction, which is you do not do whether you do a single Froeck curve, where you could do that offline with your baseline correction. Therefore, you have an advancement of real-time data analysis versus doing everything offline later. So this results in a faster speed and higher resolution image. You have an accurate force control and gentle tapping on the surface. So you, again, not pressing too hard into your surface, because you are setting, or the system sets up a set point where this behavior is as linear and repeated as possible. You have a real-time high resolution, and in addition, a mechanical properties mapping. So this is a huge difference to older methods, which were at that point called force volume, where you basically measurement would take hours to complete a force mapping of your surface at lower resolution, and now an image can be done within the same amount of time as a standard tapping image. So we have various data channels from that. So first we have the height information in the image. We can get the modulus, which is basically, again, as said before, the linear part here. So is calculated from the linear part here. You have the deformation, which is the difference between the zero force surface meets the retract curve towards the maximum indentation or deformation inside. You have an adhesion, which is again the measurement from the lowest point to the zero line, and you can also get an energy or dissipation of the material, where you can see where the energy from the tapping is moving to, which is actually the area underneath the curve. Deformation, again, so a softer sample has a higher deformation. The deformation calculation is using the approach curve. Usually this deformation underestimates the indentation by theory, and here's one of the main points here. Since the deformation is based on the separation plot, it needs accurate deflection sensitivity calibration, and this is one of the crucial points for PeakForce QNM. You have to measure the deflection sensitivity accurately, usually on a very hard surface like the sapphire, which is sent with a calibration kit. Here you can see the indentation is from the snap into contact till the end of the hard wall contact. And here's again, this is about the sync distance. This is also an important parameter. I'm talking about that more tomorrow, but basically this means this is a time constant, even if it's called distance, it's a time constant during each cycle when the cantilever reaches the lowest position. So basically when it's no force and the maximum force here, and this time in between is called the sync distance. Sorry. On hard samples, the deflection reaches the maximum when the piezo extends to its lowest position, so you should also calculate that, or this should be calculated first on the hard substrate as the sapphire. In QNM analysis, the sync distance or peak force position is used as the turning point between approach. In approach, the force curve, again, the sync distance or peak force position is used as a turning point between approach force curve and the retract force curve. So then they are put on top of each other as in the standard force curves. Like here in the image down here, and you have the sync distance is also can be problematic, put it this way. So you can, if your synchronization is incorrect, like it is too late, you see that the blue curve and the red curve do not lie on top of each other, which should be the case if it's a real standard behavior for a hard wall contact. This contains the decreasing force before the turnaround and might not be a problem, but it could be that it's you have some viscoelastic behavior in there again. So if it's too soft and your tip is too stiff, this might be the case. If it's too early, then your retract curve contains the increasing force at the beginning of the turnaround, which means in the end that your image of your surface will not be correct. Inside our software, we have a button which is called auto configuration, auto config, which you should use on a hard sample to measure the sync distance. Overall, we have various sync distances in the software. Meaning, so in version 8.8 and 8.1, 8.15, we have one value where you have to manually transfer the data for later correct analysis because you need the sync distance for accurately measure and calculate the modulus. Meaning, if you measure your sync distance on Sapphire, you should write down the value in version 8.15 and lower. And then when you're on your sample where you like to measure your modulus, you have to type in the number by hand. For version 9.3 and 9.4, you have two different ones. One is the sync distance QNM value, the other is the sync distance new value, because the sync distance is in the first approximation, if you're not interested in absolute quantitative values, it is adjusted to the material you are measuring at the moment, because this is where the difference comes into play. The second parameter I'm talking about today is then the peak force set point. And overall, again, so this can be changed when you're on the surface, and it's okay to engage with all what I did in my example, with all set point gains, gain rate, and Z limit to on. So everything is adjusted by the system itself. But after you are engaged on the surface and you have stable conditions, so you're nicely seeing your surface, you should turn off the auto set point. There are two reasons. So one is, again, if you have different materials underneath or on your surface, and you're interested in the modulus, you should have a constant set point to then derive proper values for the different materials. And it is also used, of course, to control the indentation depth. And therefore, the contact area, speaking the effective tip radius, depends on the indentation depth. For DMT, again, you should just adjust your set point to have at least 2 to 5 nanometer, better 5 to 10 of indentation for DMT, so for harder materials. For SNEDON, meaning softer materials like cells or gels in liquid, the indentation should be larger, 30 nanometers or bigger. But this has nothing to do with the peak force engage set point. which is set by the software beforehand. So, and there it doesn't matter because this is what the system is doing for the very first measurement. So it wouldn't matter if the scan assist auto set point control is on or off. And for the engaging, again, the PeakForce engage set point is used, and you can find that in the engage parameters. And the default is set to 0.15 volts, which is okay for a soft cantilever, meaning low spring constant like scan assist air, but it is already too much for a stiffer cantilever, for instance, like the R-TESPA, which might then already punch a hole into your surface, which is maybe not repairable. So therefore, if you're using R-TESPA probes or even the R-TESPA 150, R-TESPA 300 or even stiffer, please use PeakForce engage set point of 0.05 volts. One other parameter here is the amplitude, which you can adjust. Usually the amplitude is around 300 nanometers by default, but the amplitude combined with the set point determines the contact time ratio, meaning so it is better to have a longer contact time of the overall force curve of at least 10 to 30%. If it's too short, as you can see it on the top image, you have less data points there, and therefore you might not get good results or more errors in your QNM measurements. But sometimes a higher amplitude is needed to overcome large adhesion forces. In addition to that, you have also the frequency. Usually, again, the default is for icon and multi-mode is usually 2 kilohertz. For the catalyst and resolve, it's 1 kilohertz. And even for the multi-mode high rate or the fast scan for the icon, it can go up to 8 kilohertz, which gives you nice and fast topography images. But the lower frequency, you have more data points in each force curve, which can give you much better modulus information. And the lower frequency is also preferred for measuring in fluids, therefore, because you have less hydrodynamic background there. And our DSP usually analyzes the force curves at 1 kilohertz with the current software versions from 8.15 up to 9.1. I have honestly to check if it's the same for 9.2 or 9.3 or 4. Here's something about the PeakForce capture mode, where you can basically capture a force curve with each pixel measured. Therefore, you have to, this is valid for version 8.15 and higher. You have a button where you can press on it, and basically then you can see your force curve. This force curve icon, your standard capture icon changes from the default to the one with where you can see the force monitor in here. Please be aware that you check because if you press the button while it's doing the scan, you have to wait for a full frame to also capture all the force curves. Sometimes you get a small message that you only get every second force curves because of the data density there. Usually it should be done one force curve at each pixel. With that, the advantage is you can change afterwards in the offline analysis, even there still your spring constant, for instance, or your radius, if you measure afterwards to get the correct readings and recalculate your data. This is actually for today, and I'm open for questions. Tomorrow it will be more about QNM, calibration, and image optimization. So I'm open for questions now. Hello? Not sure where the moderator is. Okay, I see some questions, sorry. From Jorge Rodriguez. Many published works uses soft cantilevers 0.06 to study stiff viruses. I've always wondered myself, is it okay? So basically, again, the question is possibly yes. Depending on, again, you have to have indentation of your surface and deflection of your cantilever. If this is the case, then it can work. I think these measurements were done in contact mode, maybe even. So I'm not sure if they were done in PeakForce QNM. I see. Okay, maybe. Okay. This is more for the presentation. I didn't see anything about that, sorry. Okay. This was more about the presentation. I'm sorry for that if there was a mishap with a camera, maybe. If I use a TAP 150 probe, is a PeakForce set point of 0.25 volts a lot for biological cells? I would start again with something like 0.05 to start out, and then manually increase the set point to get a good force curve at lowest possible values. So for instance, like DNA or something like that, you can have a set point of, for a good imaging of, let's say, 100 piconewton can work. Would you think that a given calibration has a life span from Rainer Lischke's calibration? So basically the main thing is the deflection sensitivity, and this usually changes already if you change your laser positioning. So yes, during a measurement, even then, I would from time to time check the deflection sensitivity just by the small button which allows you to recalculate it, or you don't have to go to a very stiff material, because it can be, if you're in liquid or something, then you can work in the liquid also and check if you have a huge change of your deflection sensitivity over time. So there is a lifespan for a calibration. In PeakForce capture, the captured force and average curve in the pixel, or is the captured force curve an average curve in the pixel, or is it on out of all in the pixel? So if I could understand this correctly, so basically it is an average. So if you imagine you have 2,000 force curves per second and you have 256 lines, so it will be averaged. 256 lines per second for your data, so it will be averaged, yes. Could one calibrate today and measure tomorrow? Your spring constant should stay the same. Again, deflection sensitivity, I would just do it just before the measurement. Spring constant should be fine. I am testing from Ahmed Khazali. I'm testing elastic models of animal soft tissues in air by using TAP 300, almost fresh. What is the recommended method to calculate the modulus and DMT or Sneddon. So please have a look at your indentation depth. If it's smaller than or somewhere between 5 and 20 nanometers indentation, you would use DMT. If it's larger than 30 nanometers, I would use Sneddon. Is it possible? This is the next question from Abdelia El Arasi. Is it possible to detect the thickness of a soft layer on top of a little bit harder sample? For example, a nanoparticle with soft covering material. It slightly depends on if there's a huge difference between the two of them. I think you can see the different layers. The thickness will be a bit more tricky because, again, if you stay at one set point, which is good for the QNM, you will have different indentation and therefore different heights displayed in your image. It is possible to see the single softer material for the correct height. You would need to adjust your set point to very, very low values. What could be the main difference? That would be next question from Miguel Urbano. What could be the main difference compared with intermittent indentation? I'm not sure if I understand this question correctly. However, the difference between indentation measurements, like with the Heisitron system or something like that, is that we have, again, also the deflection of the cantilever in our measurements, so it's not the perfect values. However, if you calibrate the system properly, your values are pretty accurate. Sorry, I'm not sure if I pronounced the name correctly. Rakhavendran, my cells have a width of 4 micron and a height of 1 micron. It should be okay. For measurements, next question is possible to conduct PeakForce QNM at DI-CP2 SPM? No, from Alexander. So the only systems capable of that are right now the Icon, the multimode, and the Catalyst, and the Resolve system. Even the Edge is can possibly do a scan assist mode, but it is limited for the QNM part. Question: is it correct to assume that the tip radius stays constant during measurements from Alicia Nuez? There's a way, and I'm discussing that tomorrow, to calculate the radius. There's a method for it. We have a tip check sample with the calibration kit, and you can simply try it. Usually, if you're not pressed too hard, the radius wouldn't change. The radius itself, so meaning the contact area, which is used to calculate the modulus, will change if you press harder into the surface. But overall, the tip itself, if it's done properly and not too aggressively, the tip radius shouldn't change. Next question from Sri Rajadurai. Hi, if the frequency of PeakForce QNM command is close to the resonance frequency of the cantilever, usually that's not the problem, because PeakForce QNM again is at 2 kilohertz or 1 kilohertz or lower, and the standard resonance frequencies usually are in the range of, let's say, 20, 80, 200, 400 kilohertz, so you are far off from that. What else do we have here from Amit Kanzani? What is the range of deflection sensitivity values when we use TAP 300 probes? This depends on the system. This is basically slightly different between an icon and a multi-mode at least, and for sure also for the catalyst or resolve system. But this usually it shouldn't vary much between the probes you're using in there. I would have to look for a number, but right now, also depends, of course, on the but let me just check. Maybe I have something on the screen for the calibrated probe I used before. So for instance, if I remember correctly, for the icon, it's around 70 nanometers per volt, give or take. Question: is the frequency of PeakForce QNM command? Okay, this was already. No, it's not close to the frequency. It should be far off. Next question is: am I correct that scan-assist air probe is not usable for PeakForce QNM for silicon sample? How about for bacteria? This is from Havendran again. So. Yes, scan-assist air should be good for bacteria, roughly. Again, not on a very stiff surface, but if you have bacteria on the stiff surface, again, you might sacrifice your mechanical properties of your silicon, but it might be good for your bacteria. So next question: how can a property like adhesion, a stochastic event, be extracted if multiple curves are averaged at each pixel? That's a good question. I cannot answer right away. I will check into that. Please really send me an email and I will look if I find an answer for you. Question relating to sprinkling constant accuracy needed for reliable experiment. Most probes come with a reasonable height deviation from the nominal quoted value. IO test per is nominal 26 with a minimum max between 8 and 57 from Lucas. Give a force curve that is 9 times 3. Is there a cantilever that you recommend with a much tighter tolerance? So for the new software, actually, we have a software version 9.4 where it is possible. This is right now valid for the icon, I have to say. For multi-mode and resolve, I haven't heard anything yet. It's not released for them, but for the icon it is. And there you have pre-calibrated cantilevers, where you have the spring constant is derived from the frequency by the vibrometer, and also we have a predefined radius for them, and they are put in a box which is barcode readable. So you basically just select now your and the variation of the radius is really small. They have a radius of about 30 nanometers, and depending on the probes you select or the spring constants you select, again, they're in the same range as scan-assist air up to R TESPA, but much more defined. So this would help you there. Other than that, again, so if you have problems with probes like R TESPAs, R3, which are made from Bruker, and you purchase them from us and you say, hey, the results are not reliable, please contact us and we will check if we have a production problem there and might compensate you for that. Is it next question, or should I continue, or should we stop here? Okay. Just ask there a couple more. It's just a bit more. It is possible to measure any mechanical properties by non-contact mode. My personal answer, so I'm not completely sure, but I would say non-contact mode, it will be tough because you don't get a proper force curve and you have some hysteresis in your force distance measurement there, even if you do not touch the surface, and therefore it is very unlikely that you can get mechanical properties except for soft and hard from it. So no quantitative measurement there. Next question from Vinay. I'm sorry, this can be a silly question, but what is the reason behind stating that the cantilever deflection should be less or equal for the indentation? Can we do the following? You will get the presentation and then we can discuss offline. I think that's easier. Almost done with the question. Is there a difference between Ike and Fasken measurement capabilities when it comes to QNM? Does it matter which scanner one uses? First, easy answer is no. Okay. Okay, I think that's it so far. There's one again, Bettina Zimmer, please contact me offline. I think that's easier right now. Okay, I think that's it.
Okay. Thanks, Christian, Froeck, and thank you all for attending today's webinar. And at the end, could you please spend 1 minute to fill our small poll? There are only 3 questions. And the first one is, what best describe your station? The first is learning, second is searching, the third is investing, and the last is purchasing. And thank you for your cooperation. And now let's move to the second one. Do you find the presentation is related to your research? Okay, let's go to the last one. Would you like to participate in our other webinars in the future? Okay, great. Everyone, we finished today, and we appreciate you being here. And thank again for joining us today, and we will see you tomorrow for the QNM Part 2. Have a nice day. Bye.
Bye, guys.